Welcome everyone. Today's lesson will be on AC and RLC circuits. I was muted. Yeah, sorry, my bad. Okay, yeah, but anyway, I'll be starting right now. Today's lesson is on AC and RLC circuits. So, okay, this topic usually is not actually that common in like SPhO, honestly, because I don't know, it's just generally a trend that it doesn't come out too much. But I still suggest you pay attention because it's still a good skill to have, and it's a good way to apply all the knowledge that you have from the previous chapters. And they also come out in more advanced Olympiads like AFO and IFO. Like if I had to give an example, um, when I went to AFO 2025 this year, the experiment round was AC and RLC. So just telling you that these topics can appear anywhere, wherever. Okay, so like it's always good to have the knowledge of all of them, even if they don't come out very often. And also RLC, I guess, kind of came out in S4 last year also. So it's good to be prepared lah. Yeah. I don't anticipate this taking too long. If the lesson ends early, don't be too surprised. But if the lesson also extends to 2 hours, I could just be slow. I'm not too sure. But yeah, that's just a disclaimer before we start. Okay, yeah. So anyway, okay, let's just start. So first thing I should be introducing is obviously the main circuit elements. You should have learned in the previous classes about resistors, capacitors, and inductors. These are your main three elements that you'll be dealing with in this chapter mainly. Yeah. I mean, that's what RLC stands for. RLC stands for resistor, inductor, and capacitor. They are the symbols for each. Yeah. So I guess just to introduce them first, right? They're governed by these three equations. You should have what's wrong with that? You should have learned this in the past. This is your Ohm's law. This is your definition of capacitance, and this is your definition of your inductance. So these are the equations that you're going to be seeing a lot today, and you need to have these to heart. Ignore the fact that there's no diagram, but usually they'll be indicated like this, and like this. These are what your circuit. These are what they look like in a circuit. So it's good to remember. I don't know what's wrong with my pencil. Sorry. Okay. I guess there's some box here, but it's fine. Yeah. So these are what they're interpreted like. And yeah, you need to memorize these equations. And usually there is a sign convention which you need to take note of. It's not very strictly necessary, but if you want to keep to these equations, then it's really important to know something which we call the passive sign convention. So how the passive sign convention works is that, let's say you have a circuit, something like let me think. Okay, let's say you have a circuit something like this. Okay, you have a battery and you have a capacitor here, and here this is the negative terminal, this is the plus terminal, right? And let's say we take this to be the negative and this to be the positive terminal. Okay, so what we're gonna do is we're gonna let some current I flow through this circuit in this direction. Okay. Wow, this iPad. Sorry, yeah. So how the passive sign convention works is that if your current travels in the direction of your potential drop, then any equations that have your I and your V are going to be positive. If not, then they're going to be negative. So, for example, in this case, right, since your current is flowing in the opposite direction of potential drop, because clearly here it's going from minus to plus, right? You then assign your equation to be I to be minus C d v dt here lah. The reason just being that, again, your current flows in the opposite direction to potential drop, which is potential gain lah. Yeah, this is the passive sign convention lah. If you wanna make sure that your signs are correct all the time, you are very very strongly recommended to follow a convention, and this is the convention that some of us usually take. It's very helpful lah. Yeah. The whole detail should be written here lah, so you can always read it again if you don't remember how to. But yeah, that's the passive sign convention. But yeah, And any circuits that involve all these components, we call them RLC circuits, as I've talked about just now. Okay, next thing is voltage and current sources. Voltage sources are what you typically see lah, and they are notated like this lah. This is a voltage source lah. On the other hand, right, you have current sources. Sometimes they are labeled like this. You don't see them very often, but all they do is just they impose some current through lah, like I, something like that lah. Yeah, it's not too deep. I think you've seen this before. You've seen it in RLC. You've seen it in DC circuits. You should see them here now. So probably not current sources a lot, but sometimes they can appear also. And switches, I think it's very, very self-explanatory. This is what a switch looks like. This is when it's open. This is what a switch looks like when it's closed. Yeah, and when it's open, it just acts like there's no wire there. And when it's closed, it acts like there's a wire there. That's pretty simple lah. But that's mostly all the elements you'll see today. There sometimes might be other elements that you might see sometimes. Sometimes you might see something that looks like this. This is something called a transformer. Or sometimes you might see something like this. This is a diode. But you won't encounter them very often, if at all, honestly. So you don't really need to take note of these. But sometimes you might see them in more like advanced competitions. Yeah. Okay. So those are the main circuit elements. Next, the first thing we shall go through is first order circuits. Okay. I'll go through this really quickly because honestly a lot of it is just math. And actually a lot of this chapter is actually just math. But okay, first order circuits, they usually involve either one capacitor or one inductor that's in a circuit. Sorry, they usually only have capacitors or inductors in the circuit. So just to consider one very simple example first, let's consider a basic RC circuit. Okay, so what we have is a voltage source with EMF epsilon with a resistor R here, as well as a capacitor C here. So this is what our circuit looks like. And what we're going to do is we're going to analyze it. Okay, so how we do so is that, okay, sorry, I forgot this was a switch, but we have a switch here, and what we're going to do is at t equals 0, we're going to close this switch up. And what we want to do is we want to investigate the time dependence of the circuit lah. So what exactly do we do? Sorry. Yeah, what exactly do we do? First thing we're going to do is that we're going to apply the equations that we have now. So the only equation that we have here is your I equals C dV C over dt. And okay, I mean there's another equation now which is pretty clear as that of the Ohm's law from the resistor. But this is the one involving the derivative. And here we've taken the sign convention, which is like I think here we've taken this direction. Yeah. Then what we then do is we apply Kirchhoff's voltage law on the loop lah. And we just said this equation and we get this. I'm not going to elaborate too much. This should be pretty obvious how you got it. And you've learned the DC circuits chapter already. So I think it should be pretty clear how you got there already. How do you know which is the positive and negative side of the capacitor? That one usually you set some convention lah. But here in this case, since the charge is like here we're defining the current to flow out of the positive terminal and into the negative terminal. So we're letting this be your the charge because yeah, obviously the positive charge is going to accumulate on this plate, and that allows us to give the positive sign here. Yeah. Okay. Anyway, so now that we have this, right, we can just substitute this into this and we get this equation here. And this is a really simple differential equation. I think you should know how to solve it. But yeah, this is a really simple equation. You should know how to solve it. And we get that this is actually an exponential dependence. And we can also solve for the current by just substituting this into this. So this is what we call the charging RC response. Because here what you're essentially doing when you flip the switch is that you are charging the capacitor up to some charge. and once it's at equilibrium, your voltage of this capacitor will have the same voltage as that of the voltage source. That's why we call it charging. Yeah. And I won't go through the details, but the exact same situation happens when once you have it fully charged, you flip it back. In which case, you now call it the discharging RC response. And you get this equation, which is just from this, but this time you don't have the voltage source, etc. Yeah. So that one is not too difficult, honestly. Yeah. So one very important characteristic of this charging and discharging circuit response, right? This is something you're going to need to remember, okay? This is something we call the time constant, okay? So the time constant is something that describes the speed of the exponential response. So here we define the time constant as RC. The reason is because you can see the RC is on the denominator here. So usually when we say the time constant is something, right, it means it's usually proportional to something like this. Like you say some quantity is proportional to this. Yeah. And basically it sort of means the time it takes for a quantity to reach like 1 over e of its value. So time to reach 1 over e of the initial value. That's what the time constant basically is. Yeah. And basically for all exponential dependencies, we'll use this time constant as a way to quantify its speed. And we'll see another instance of it later. Yeah. And just keep this in mind for now. For time constant of a circuit, of an RC circuit is RC. Yeah. Then the next example is an RL circuit, which again, this is the same circuit, but this time we take the capacitor and we replace it with an inductor like this. Yeah, this is our inductor, and there's also a switch here. Yeah, there's also a switch here. Yep. Okay. So this is what your circuit looks like. Just ignore the fact that it's ugly because my pencil's going crazy, but never mind. So I won't go through the derivation too in depth again. You can read it yourself. But basically we apply the same equation again. Oh my god. The same equation again. What is wrong with this? Okay. Okay, but basically we apply the same equation. We apply Kirchhoff's voltage law and we get that lah. Yeah. And then this is also a hello. This is also a linear differential equation which can be solved quite easily. And you can get this. And this is what we call the energizing RL circuit response. And similarly, we can do the same thing when we get rid of this voltage source and we close the switch. In which case we can get this. This is the de-energizing RL circuit response. I again won't go through it in depth, but the one thing we gotta note is that now we have a different time constant for the circuit because this circuit has a different charging and energizing and de-energizing rate. As you can see here, right, this is of the form minus t over L over R. So this time the time constant is this. Yeah. So yeah, that's what the time constant. That's just a basic example of how you apply these equations in a setting where you want to solve like for the time dependence of something. Yeah. Okay, give me a moment. Me! Me! I'm busy. I'm teaching something. Okay, sorry. So okay. So now you've gone through that, right? Now I'll go through some general circuits which only involve one capacitor or inductor. So basically, what we do is that, okay, let's say we had like some really complicated circuit, okay? Looks something like this. And let's say we had a resistor here, resistor here, resistor here. I don't know, but like it looks really complicated. Let's say we have a really complicated circuit. What is wrong with this pencil? I don't know if it's a pencil. I don't know what's the issue. Okay, whatever. Let's say we had some really complicated circuit and we wanted to solve for like the time dependence. what you could do is you could apply Kirchhoff's laws or mesh analysis or something. We let some we let the current through something be. Okay, sorry, just give me a moment to settle these issues. Okay, whatever, but you get my point lah. Basically, let's say you had some really complicated circuit and you had a lot of resistors and stuff like that, and your goal is to basically solve for the time dependence. It might seem really complicated to apply Kirchhoff's laws, especially if you had many loops and stuff, but there's actually a theorem, there's actually a corollary which allows us to really quickly determine the time dependence of something which only involves one capacitor or inductor, which basically states that if you have a circuit which only has voltage sources, current sources, resistors, and a single capacitor, right, your time dependence is always going to be a linear function of an exponential in time. What that means is it's of the form a plus b e to the minus t over tau, something like that. And that you can say that for like any quantity lah. That's either v or I. Yeah. And this time constant of the circuit is going to be this. It's going to be one of this. It's going to be either RFC or it's going to be L over RF. And this RF is your effective resistance across the terminals of the capacitor. Yeah, or inductor. So basically, for example, right? Yeah. But basically, for example, right? Let's say you had a circuit which looks like. Let me try to figure out these problems. Sorry. Let's say you had something like. Let's say you had something like this, okay, and you want to find the time constant. Okay, let's say these all had equal resistances R. Okay, to find the time constant of this circuit, right? All you'd do is that you'd find the effective resistance across the two terminals of the capacitor. So basically, what you effectively do is you kind of get rid of this battery because it doesn't really change the effective resistance, and then you just calculate the effective resistance from there lah. Yeah, and it's not really too difficult to do so lah. Yeah, I'm not gonna do it here. I really cannot be bothered. But I think it should be pretty obvious how to do it. Yeah. So that's what the corollary says lah. And if you know Thevenin's theorem, it basically comes from that lah. It essentially just means that if you have any circuit consisting of resistors or something like that, then of resistors, voltage sources, and current sources, you can eventually collapse it into some very simple form involving only one battery and one resistor. And then once you have that, you can basically apply the basic analysis that I've gone through just now. But yeah, but I won't go through in detail. But basically, it's a very useful fact to know that this is the thing. So, and this gives us a really easy way to solve for time dependence of parameters. For example, so the process would be like you calculate the time constant, which is just one of this, right? Then you can determine the initial and limiting final values, and then you find a linear function of the exponential in time. So I won't go through this example, but you can read it for yourself. It's basically just you find the time constant by finding R effective, which is 10 seconds in this case, and then you find the initial and final values. And to do that, right, in this case, right, your initial value is that because before it was flipped, right, it was open. So if it was open, right, initially it was closed, then it was open at t equals 0. So before that, right, since it was closed, right, you'll just want to find the potential difference across the capacitor charge this up. And to do that, all you can do is you can just apply the potential divider rules, you get this. And then your final value is that, obviously, because your voltage source here is been disconnected is from the circuit essentially, because your battery is here, and when you disconnect it, right, it's basically gone. So all your capacitor doing is discharging, and your V infinity should be 0. Then all you need to do is that you fit that to an exponential time dependence like this, and you get that this is your function for Vt in terms of for V in terms of t lah. Yeah, and that's basically a really simple example lah. Yeah, and I will not elaborate any further, but that is pretty simple lah. Yeah, so this is another example. I won't talk about it too much, but yeah, essentially same thing. You are calculating the effective resistance, and you get the time constant like this, and then you can calculate the initial and final currents, which in one case you have the current that flows through here, and in the other case you have the current that flows through here instead. So that's just a simple case of Ohm's law, and then you can then fit it to an exponential time dependence like this by taking the initial and final and then plug it in into this, and you get this is your final output lah. Yeah, and a very useful thing to note for these questions is short and long term behavior, where basically, right, because of these equations, since your current and your voltage cannot like diverge or cannot be infinity or minus infinity at any point in time, because that kind of means your circuit is basically gone, bro. Like, if that happens, right, because of that, right, these equations must imply that these are true. Your voltage across a capacitor and your current across an inductor must be continuous with time lah. Yeah, and because of that, that allows us to deduce the short and long-term behavior of these circuit elements after some sudden change, which is, for example, a switch being flipped. So, for example, for a capacitor, its voltage right after and right before the change are the same, and the current after a long time is 0. This one comes from the fact that that's just equilibrium lah, because at equilibrium, your V is no longer changing, so your dV dt is 0, and that means your I is 0. Yeah, and the same thing for this. So this is a very useful thing to know when you're solving circuits involving these circuit elements are. A nice way I like to think it is that, for example, right, at equilibrium, right, once these things are completely charged, right, like, yeah, once these things are completely charged and they're at equilibrium, this thing is basically open. I mean, that's kind of obvious because these things are like disconnected, right? So like this thing is basically open at equilibrium. And when you just flip a switch, it's going to be the opposite. So it's just going to act like it's a closed switch. And like it's a closed wire. And similarly for inductor, right? When this thing's at equilibrium, it's basically just a really, really long wire. So it's basically closed. It's basically a closed. And similarly, the opposite is true for right when you flip a switch. So it's going to be open at the start. Yeah, that's how I like to memorize it. But it really depends on you. Yeah. And that's basically it for RC and RL. There's also general first order, but I won't talk about it too much. You can read this example on your own. Okay, I know I'm asking you to read a lot of examples on your own, but since I want to condense the lesson, I don't really want to talk about it too much. But this is an example where you have multiple capacitors, and you do actually need to solve for the explicit time dependence using differential equations, which is a bit unfortunate, but that's what happens when you have more than one capacitor. All you do here is you apply Kirchhoff's law, and is that you apply Kirchhoff's law or mesh analysis in this case. And I wish my pencil would work at all. Yeah, but you apply mesh analysis and you get this, and you can express it in terms of the charges like this. And someone asked me why this is positive while this is negative. The reason is because of the sign convention that we take lah. For example, if we let the currents be like this, right? Then we let the charges on the capacitors be like this. This is what we've defined lah, basically, for our mesh analysis, because this here is positive. So this is like that. Then the reason this becomes negative is that because when your current is positive, then positive charge builds up on this plate, and that decreases your charge. So that causes so basically a positive current corresponds to a negative dq dt lah. That's why your signs flip. And I won't go through the rest in depth, but basically how you can solve these coupled system of differential equations is you can actually just add and subtract both of them, and you get that they're now a first order linear differential equation which you can solve like this, and which gives you this and now you have the explicit time dependence which can then be used to solve the max chart, which is just math. I won't go through it too much, and these are just the kind of the normal modes ish, etc. But yeah, whatever. But yeah, so if you have general circuits like this, they probably won't appear in SPhO, I don't think. But if they do, it's a good skill to know how to apply what you've learned from DC circuits, as well as the equations for the all of the circuit elements together, and then to get differential equations which you have to solve eventually. Yeah. The next part is about second order circuits. This is also going to be quite brief, but the first thing we shall analyze is a basic RLC circuit where we have a battery like this, epsilon, and we have a capacitor in series with an inductor. Let's say that's an inductor, LC. Okay. So how exactly do we solve for the circuit response? Again, we get the two equations that we need, which are these two. We apply Kirchhoff's voltage law. Actually, here it seems we didn't have a battery, my bad. But we just have both of these together, and one of them has initial voltage. And when we solve for this, right, how we get from here to here is that your VL is L di dt, and this di dt is obtained from the derivative of this. So that gives you this when you solve. And this is a second order linear differential equation. And actually it's just simple harmonic motion lah. Because you can see that that's just, oh my god. You can see that it's just VC double dot is minus 1 over LC VC, which is, this is just SHM. So you know that your dependence is going to be sinusoidal like this, basically. Yeah, and from there you can just solve for your required quantities in terms of the initial conditions. But my point that I'm trying to make through this example is that this basically acts sort of as a spring mass oscillator. So this is sort of, if I could draw at all, right? This basically acts as, please, yeah. This basically acts as a spring mass oscillator in a way. Yeah, because you can kind of understand that in a way if you consider the total energy of this system, because the total energy is half kx. Sorry, your total energy of the system is half, is it q squared? I cannot write with this pencil. The total energy is q squared over 2c plus half L I squared, and you know your I is your derivative of your charge. Oh my god. Let me see if I can draw with. Let me see. Give me a second. Okay, whatever. But basically, your total energy is this, right? Q squared over 2c plus half L Q dot squared, because your charge is the derivative of your time derivative of, sorry, your current is the time derivative of your charge. And that's analogous to a spring mass oscillator, because that of a spring mass oscillator is half kx squared plus half mv squared. So this is analogous to this, and this is analogous to this stuff. Yeah, that's kind of what I'm trying to say. And that is also relevant when we get to basic RLC circuits, because your R acts as a dampener, basically, like similar to that of a spring mass oscillator. So in this case, right, now we have a circuit that looks something like this. capacitor here, a resistor here, and an inductor here. And what we're going to do is we solve for the time dependence again, which again, we apply these same equations and we get this, blah, blah, blah. But now we have a second order differential equation. And this is actually where our knowledge from oscillations comes in. Because this is actually the equation for a damped spring mass oscillator, as I've said just now. Yeah, so this is actually a damped spring mass oscillator, and that's where our oscillations knowledge comes in of damped oscillations. And that's where we introduce these quantities again, which are your gamma and omega naught. This gamma is something we call the damping coefficient. It's just half of this. And this omega naught is your undamped resonant frequency of the circuit, which is sort of the frequency in this case, basically. And yeah, and we can also define another parameter called the quality factor, which is this quantity here, and it sort of quantifies the fraction of energy that's dissipated, but it's not really too important. But it's a dimensionless constant. And using our knowledge of oscillations, we can have these three cases again. We can either have underdamped, critically damped, or overdamped oscillations, and they take these forms respectively. This one you can go review your oscillation chapter if you need any help on this, but that's you need to apply your knowledge from oscillations back to here. So to give one example, which is here, basically what happens here is that you have a switch that's initially closed and you open it here, which exposes this RLC circuit here, because now no current can flow on the other side, right? So what we do is we then calculate the corresponding damping coefficient and resonant frequencies, which results in this, right? And since we have this damping coefficient is less than the omega naught, we have our circuit is actually underdamped. And since your circuit is underdamped, you have your oscillation frequency to be this, and your VD to be this, and from there, right, this is your voltage, right? We can take the time derivative to get this. And the reason we want the time derivative is then we can then apply our initial conditions, which is that your switch is closed for a long time before t equals 0 initially. So because of that, we can get these by just looking at the circuit, right? Because this behaves as an open circuit, so you can basically ignore it. And this behaves as a closed wire, so you can basically join it. And then from there, you can get these equations. And your second equation gives you dv dt at 0, which is this. And from there, you can plug them into this to get that. And you can finally solve for your quantities here. It looks kind of disastrous, but that's because we're using numerical values here. So it's not to worry. As long as you have the math down and you're very careful, you should be able to do this quite easily, and it should be quite systematic. Yeah. So the main thing to take away from this is that you gotta remember your being underdamped, critically damped, and overdamped stuff from the oscillation chapter, and you gotta be able to apply it here in this case. And for general RLC circuits, again, this is where you need to apply your differential equations again. This is where you have to manually do it, which is kind of a no choice thing. So in this example, instead we have a parallel RLC circuit instead of a series RLC circuit. And in this case, we have to solve for the time dependence again. But again, this is all the same stuff I've discussed just now. Here we're using nodal analysis instead, because it's easier to consider the potential here, since the potential difference across all of this is the same. So you apply nodal analysis to get this, and we notice this is another second order differential equation, so we can get the corresponding damping coefficient and the quality factor, and we get the corresponding solutions. And here they ask for if a series RLC and parallel R prime LC circuit have the same quality factor also, we can just equate the quality factor here and we get this equation. Yeah, that's not too important, but the main thing to take away is just how to solve these equations. Really, it's honestly the same thing over and over again, so I won't talk about it too much. Now we get to the more important part, which is AC circuit. So okay, so just now we've previously discussed RLC circuits, which usually involve some constant voltage source. It doesn't have to be constant, because if you have a time dependent source, right, you can always just solve for the time dependence as usual, except your differential equation will have that function of the voltage source. But in AC circuits, right, usually your voltage sources that are there are alternating current, something called alternating current voltage sources or AC. So yeah, these usually have AC voltage or current sources, and they are sinusoidal in nature. So I think you know what sinusoid looks like, but like these are sinusoidal in nature, and it actually turns out that these are easier to analyze compared to DC or RLC circuits because these there is a property of sinusoidals time dependence that makes it much easier to deal with. And that's where we sort of have to introduce this concept called phases. So here, this is a motivational analysis, but it's not too important. This is basically just illustrating how you'd solve an AC. This is how you'd solve an AC circuit without any knowledge of like phases and stuff. This is where you construct the differential equation, which is the same as the one I illustrated previously. But this time you have this time varying component here, which varies sinusoidally. And this consists of two contributions, which is a transient and a steady state response. The transient response is sort of the solution that we gave over here, because the transient response actually corresponds to the homogeneous solution. So that gives you all this bed damping stuff, which is not too important actually, because usually in AC circuits, we only really care about the steady state response, because the steady state response corresponds to a particular solution to this differential equation. And usually, when we want to solve for a particular solution, we guess something of the form this, because these are sinusoidal functions, and when you differentiate sinusoidal functions, you get another sinusoidal function. So that's quite easy. So you just need to guess a sinusoidal function, something like that. And you could do all that stuff, or what we're going to do is that we're going to introduce something called phases, which will massively simplify our analysis. It basically turns any AC RLC circuit you have into a DC circuit. Like really, is that powerful? Unfortunately, at the cost that we're going to be using complex numbers. And just a disclaimer here, I'm going to be using j to be -1 here. It might be a bit infuriating to you, and honestly, I don't care, because I am also a little bit infuriated by it. It is an engineering thing, but yeah, that's just a note. We don't want to confuse it with current, which can sometimes be denoted as I. So just take note that when you see a j, that just means I. Yeah. So I assume all of you should know complex numbers by now. So it should not be too bad. You need to know this equation, which is Euler's formula. It's not too deep, honestly. This is Euler's formula. As long as you know this, I think this entire part should be pretty smooth sailing. But just to introduce the concept of phases, what the concept of phases is that you want to represent a sinusoidal quantity as a singular number. It doesn't really make much sense, because let's say you had something that varied sinusoidally, so it looks something like, my god, let's say you had something that varied sinusoidally, so it looked sorry, technical difficulties again. Let's say you had something that varied sinusoidally. Okay, just pretend it's a sine curve. Okay. The thing is that there are two things to describe this sinusoidal curve. One thing is your amplitude A, and another thing is your frequency. Another thing is your phase, which sort of describes where exactly it starts. There's also your frequency, but here we're assuming that your frequency is constant throughout. You don't really care too much about the frequency. But let's say you want to include some sinusoidal function that has some constant frequency as a singular number. What we actually do is we use this definition here. It looks like a lot, but basically we're saying that this quantity here is your phasor, okay? And this is what we say is in the frequency domain. And this quantity here is your actual time varying quantity. And the relationship between both of these is this, which says that your sinusoidal quantity is the real part of this phasor multiplied by this e to the j omega t lah. To give the intuition, it's sort of like this e to the, God, it'd be so much better if I could draw, but this e to the j omega t, right, is basically something that goes in a circle in the complex plane lah, if I could draw it. But it's something that goes in a circle in a complex plane. Okay, whatever. It's something that goes in a circle in a complex plane. And this phasor, right, basically describes some transformation to this vector lah. So by multiplying by the phasor, right, you get another vector, something like this lah. So this is after you multiply this e to the j omega t by this phasor. And now this phasor rotates in a circle also lah. And it rotates in a circle that has frequency e to the j omega. It has frequency omega. And then what you're doing is you're taking that and you're projecting it onto the x-axis, kinda. I still wish I could draw this, but my pen is not working. But you take this and you project it onto the x-axis, and this length would be your AT. Yeah. I know it's not illustrated very well, I'm sorry, but I hope you kind of get what I mean. Basically, you take this phasor transforms your rotating vector in the complex plane, and you project it onto like the real line, and that's your sinusoidal quantity. And the benefit about this is that, firstly, you can directly relate some sinusoidal function as a phasor if you know its amplitude and its phase. Because if your amplitude is a0 and your phase is phi, then your phasor is just a0 e to the j phi, which is quite easy lah, and I've already derived it here. And the second advantage about this notation is that your derivatives are super simple now. Why? Let's say we consider dA dt here, right? When we differentiate with respect to a real number, when we differentiate with respect to time, you take the real component here, right? This real component doesn't really matter, so you bring it out. This phasor is a constant, so you bring it out. And then you differentiate this quantity here, right? And we differentiate this quantity, this j omega comes down, and you just have that. And this is actually just another sinusoidal varying quantity. But instead, right, now you have this analogy instead. Your dA dt is j omega a. Yeah. So now, right, what you've basically done by having this analogy of sinusoidal varying functions with phasors is that you have a way of basically getting rid of the time derivatives in that sense. Yeah. Why did the omega t get left out for equation 14? Oh no, because okay, the point of this like transformation is to get rid of time dependence altogether. So this is why we say that AT is in the time domain, and this phasor is in the frequency domain. So we sort of get rid of the time dependence. So when we have a phasor, right, we are already assuming that we know the frequency omega, and that way we don't include it in our phasor expression. So there's already that implicit omega that is there lah, kinda. Yeah. So phasors don't usually include the omega. Yeah, if that makes any sense. But yeah, if that makes any sense, your phasor only encodes the information of the amplitude and the phase as one complex number, basically. So your time dependence is no longer there and is not needed in the phasor. And again, this already assumes that you know your frequency omega. Yeah. This will probably be clearer later when we actually start dealing with circuits lah. But for now, all you need to know is that some sinusoidal function with some amplitude and some phase corresponds to a basically constant number, which is called a phasor. And it's a complex number that has some amplitude and some phase in the Argand space. Yeah. So with that, we then come to this concept called impedance. Okay, so how exactly impedance? What exactly impedance is sort of complex resistance. So when you deal with RLC components and AC circuits, what phasors do for you is that when you take the analogies, right, when you convert stuff from the time domain to the frequency domain, and you apply this derivative here, what you get is these three equations. And what is the one thing that you need to know? The one thing you need to know is that these values are actually proportional to each other. I guess the pencil is deep, whatever. But these values are basically proportional to each other, yeah. And that allows us to define these things called the impedance, which basically means that if you take some circuit and you convert it into the frequency domain, these circuit elements essentially become resistors in their own way. So, and these complex resistances are what we call the impedance. Yeah. And they basically allow us to treat AC circuits as DC circuits entirely. Why? Because all you have left when you have an RLC circuit is just a DC circuit with complex resistances. Yeah. So, let me try to draw the diagram now. Yeah. So let's go back to our original example where we had sorry, just bear with me. Okay, whatever. Just imagine it. But just imagine you have an AC voltage source with time variance this, and you have a resistance, inductor, and a capacitor in series. Okay. So what exactly this allows us to do is that the first thing you do is you convert it into a phasor. So you convert the voltage source time dependence into a phasor, and that's just V0 here because your phase is 0, right? Then what you can then do is you can treat resistors, inductors, and capacitors as resistors by themselves, right? So just imagine it again. But so you have one resistor, we have one resistor of impedance R, you have one resistor of impedance 1 over j omega c, and you have one resistor of impedance j omega L, right? And once you have three resistors, right, these three resistors are in series. So the effective impedance of all three components is the sum of all the impedances. So you get this. Then what you can then do is you can then solve for the current in the frequency domain by just using the equivalent of Ohm's law here, right? So you get your I is V over Z effective in the frequency domain, and you get this expression. So now what do you want to do? You want to find the peak current. That's what the question asks for in this case, right? Like if you wanted to find the peak current. To do that, all you do is you find the magnitude of the phasor. Why is that? The reason is because here, when you take the magnitude of the phasor, right, you're basically taking this A0 value here, right? And this A0 corresponds to the A0 here, the amplitude. I can't draw. The amplitude here. So by taking the magnitude, you get the maximum current at any point in time, which gives us this expression. And with that, right, we've solved this problem without even using a single derivative or having to solve differential equations, etc. Right? And this illustrates the power of phasors. Basically, you need to solve AC circuits. Everything that works from DC circuits works for AC circuits in the frequency domain. Basically, that's what I want you to take away from this. Yeah, that's the power of phasors. Next thing I want to go through is root mean squared. Okay, actually, give me a second. Explain the last part again. Basically, when you take the magnitude of the phasor, right, what you're doing is you're extracting this A0 value. When you extract this A0 value, because again, the magnitude of this part here is just 1, actually. So when you take the magnitude, you only get this part, the A0 part, right? And when you take the analogy, right, you gotta remember that that corresponds to this A0 here. So actually, your peak current is just the magnitude lah. But yeah, this A naught here is your amplitude, which is the peak current, which is the magnitude of the phasor. I hope that makes sense. When you take the I hope that makes sense. You take the magnitude, that gives you A naught, because the e to the j phi, the magnitude is 1. And when you convert that back to its time domain equivalent, which is a sinusoidal function, this A naught is the amplitude of it. So the peak is just the value of the amplitude, basically. Yeah. So in this case, the A is a quantity, is the current. This A can refer to any varying quantity, like it can be voltage, or it could be current, or whatever, as long as it varies as a sinusoidal, very sinusoidally, basically. Yeah, so it can be V or it can be T, that's really matter. Okay, the next thing we get to is root mean square quantities. Not too sure if you learned this already, but it's basically sort of something similar to the mean lah. Your mean is defined as this, where here you're assuming that your function is a periodic function with period t lah. Yeah, and how we define it is this way lah. This is with the integral. But the root mean square value is something different, because it's basically essentially the value that is the square root of the mean of the square. That's where root mean square comes from. So that gives us this value here lah, because what you're doing inside is you're taking the average of the square of the quantity, and then you take the square root. So the reason we care about this quantity is because usually when you deal with AC circuits, we will be dealing with they will give you root mean square quantities instead, sometimes actually. So the reason we don't use the mean is because you gotta remember that your graph of a sinusoidal function averages at 0, but your root mean square does not average at 0, because that squares the value, so your entire function is positive at all points in time lah. Yeah, so typically we're uninterested in the means, but we usually care about the root mean square value, and usually they'll give you that value. So the way you convert between the two is these relations are. This is for pure sinusoidal voltages, and voltages and currents, and I won't go into the derivation because it's really just a really simple integral. But that's how you. But basically, if they give you a RMS value, you should be able to convert it to the peak value and vice versa using these formulas. Yeah. So sometimes if they give you in problems, you need to note that. Yeah. And the next thing, and the last thing I want to talk about is instantaneous and average power. So this is one subtle thing to cover lah. So let's suppose that the voltage and current through some element is defined as this. So here we give the phasor quantities for the voltage and current through some element lah, basically. And here we have V naught, I naught, phi, and psi as the amplitudes and the phasors are. So the reason our trick using phasors work with voltage and current, and we're able to solve circuits and all that, is precisely because all the operations that deal with them are linear actually. Because if you look at all these are all like linear equations. However, when you get to power is VI, or if you have a resistor, if you know, the equation can be V squared over R, or it can be I squared times R. So that's no longer actually a linear equation. So you cannot actually use phasors directly to say whatever your instantaneous power is. If you claimed it was this, you'd be completely wrong, basically. But rather, instead, right, if you want to calculate the instantaneous power at some time, you're going to have to manually convert the voltage and current back into their respective values. As you can see, it's done here, right? And you get this expression for your power, your instantaneous power. And sometimes we're also interested in the average power, because AC circuits, although the voltages and currents can vary between positive and negative, your net power can actually be positive or negative depending on whatever is being done. And if we evaluate another simple integral, right, which is just this integral over the period, we actually can get that the average power is this quantity here, which is good to memorize, but usually you probably won't be memorizing that because you don't really need to. But another thing I like to use is the phasor expression actually, because if we take this and we convert it to a complex exponential here, right, we get this expression. And how we get from this expression to the other expression is that you have this term here, right? You can actually split it by your exponential properties. You can give this part to v and you give this part to I. And this here is the conjugate, which basically takes some a plus bj, and you convert it to a minus bj. Pretend I wrote that, but yeah, basically it just flips your j component. And if you use that, right, you can actually get that this is your expression for average power. And it's a good thing to memorize, but if you are considering that of a resistor, you can honestly just use this formula instead. So your average power through a resistor can actually be expressed in terms of your root mean square quantities like this. So it's basically your normal formulas, but you use your root mean square instead. And that's another example of why your root mean square quantities are useful. And another thing to note is that the net average power emitted by a capacitor and an inductor is actually 0. I'm not going to show it right now, but if you notice that because of the equations like this, right, you actually know that your voltage and your current are actually 90 degrees out of phase, something like that. Or if you want to look at the phasor quantities, they differ by a factor of j. Because of that, when you plug in this formula, you actually get that your real component is 0. For example, right, if you consider your V phasor to be V naught, your I is going to look something like J times some other real quantity. So you multiply both of them together, you get J times some quantity, you take the real, you get 0. So that's actually the reason why capacitors and inductors do not actually have any net average power. But yeah, that's sort of a rough proof. You can prove it yourself. Yeah. And that's basically the last thing I need to cover. The example I have here is basically how you combine everything together. So to find the average power absorbed by each of the circuit elements below and verify that they sum to 0, all you need to do is that this basically is to illustrate what we've done so far. So what we have here is this circuit, and we want to find the average power by each element. How we do that is we first convert everything into their phasor quantities, which gives us this. How exactly we got there is, again, our 50 cosine omega t becomes 50 as just a phasor, and our impedances of each of the respective LC components, you see there's a capacitor here and there's an inductor here, that we can just plug into here. So we get this. So now we've converted everything into the frequency domain, and we actually get this is our equivalent circuit in the frequency domain. So now everything is actually, you can treat everything as a resistor, even though the circuit symbol is labeled there. Everything is actually technically a resistor. So what can we do? We can apply the what can we do? We can just apply mesh analysis, or I guess you can just do equivalent resistance and stuff like that. But here I didn't take that approach. I took mesh analysis. Yeah. So what we then do is we can then solve for the loop currents, and then we can get their peak values by taking their magnitudes by the reasoning that I have described just now. And from there, you can finally get the average power absorbed by each component. So you can calculate it, and you can verify that this equals this plus this. Your energy is conserved. Done. Yeah. So that's basically the whole question now. And again, as I've elaborated just now, both of these components do not contribute any average power, as I mentioned. So we only consider the resistors here, as well as the voltage source. You gotta remember that the voltage source contributes some power also. Yeah. And that's basically the whole chapter. I wrapped it up in about an hour. I'm gonna go through the problems next, but since my pencil is going through a hard time, I think I'll be switching back to the mouse. So give me a second to make the change. Just give me a second to set up. Okay. So the first question is problem 1. Actually, I haven't done the problem yet. I don't actually have to sleep. Established, and the switch is open at t equals 0. The first thing you want to do is you find the initial L just after t equals 0. Sorry. Sorry. Okay. So the first thing you want to do is you find initial voltage across L just after t equals 0. So how exactly do we do that? Sorry, I'm solving it like right now, so just bear with me. The switch is closed right before, and it's open right after, right? So, let me think. Give me a sec. Oh, right, I'm down. Because you gotta remember that from what I talked about just now, right? Your across an inductor, right? When it is at a steady state, right? This thing basically acts as a close. But right after this sudden change, right? It sort of basically acts as an open. So your initial voltage across here, right, is going to be that of the voltage that was before, I think. I think so. So when the switch here is before here, right, when the switch is closed, right, your voltage across this thing is 0. Oh, actually, no, I need to think about it. Sorry. I'm a bit crazy right now, but like, sorry, give me a sec. Let me think about it. Initially, this thing is closed, right? So this thing has voltage 18, and this thing also has voltage 18 because it's been closed for a long time. And this thing has voltage 0 volts, right? So then, right, it might be easier to pull out the solution. Give me a sec. That's weird. Okay. Sorry. Okay, I'm going crazy. My bad. So initially, right, what happens is that when this thing is closed, right, your this potential across this resistor is 18 volts, right? And the current flowing through this is 9 milliamps because that's just by Ohm's law. The thing I talked about just now is that your current through the inductor is actually continuous, right? The current through the thing is continuous. R1 is just a resistor, so it won't have 18. No, it does 18 volts, yeah. So, okay, the reason this is 18 volts at steady state is because this thing is closed at this thing is basically closed at the steady state lah. So this will take out all the voltage. Yeah. And the current flowing through this inductor is 9 milliamps. When the switch is opened, right? When the switch is opened, the main thing that to note, right? Sorry, I guess I'm a little bit dumb. But like the main thing to note is that this current flowing through the inductor remains as 9 milliamps. This is because of the thing I have elaborated in the notes previously, which is that, where is it? There. Your current across an inductor is continuous with time lah. So this current across the inductor will remain as 9 milliamps lah. And because of that, right, since this thing is basically gone, right, this and these currents are all gonna be 9 milliamps, right? So what does that mean? We have that the potential difference that's covered by this is 9 times 6, which is 54 volts, right? And the potential difference through this resistor here is 2 times 9, which is 18 volts. So what does that mean here, right? Since this whole loop no longer has a battery, right, the total potential difference across here must sum to 0. So that must guarantee that this is 72 volts and this has a higher potential. Yeah. Sorry for the brain screw up, but like basically the concept here is that you apply that the current through here is continuous with time. So right after you open the switch, the current flowing through here is still 9 milliamps. And because this loop here is now, because this section here is now gone, right? The current here flows through is also 9 milliamps. So you can get the potential differences through these resistors, and therefore the potential difference across this inductor because the total potential sum must be 0 lah. And this is in the negative. It's technically negative, but I'm denoting positive because of we want the magnitude lah, basically. Yeah. Then the second question is you want to sketch the graph of the current in R1 and R2 as a function of time. This one is not too difficult. This one is just a decay, as I've talked about already, right? So you have something like this, and it'll just look like this. These are the currents lah. Sorry. The currents will look something like this. Here your initial current. Here your initial current is 9. Here your current is 9. And actually, I got it wrong because the steady state direction is just positive. What does that mean? Steady state current. No, I'm pretty sure both are 9 milliamps. I'm quite sure. Right? What is this question, bro? What is this question? Is opened. This graph of the current in R1, R2. Okay, I don't think I really like this question because I don't know why the solutions I'm looking at, they don't really make sense. This thing is gone, but it should basically look something like this. How correct me if I'm wrong, because what I can tell is that this thing is completely gone. So it's just an RL circuit, and these things should decay exponentially like this, with your time constant being the one that's from the perspective of the inductor, which is 8 R effective, which is 8, multiplied by sorry, your inductance, which is 0.400 over your 8 kilo ohms, right? Which should give you 0.05 milliseconds, I believe, something like that. Okay, but you get the point. You basically take your time constant to be L over R, and then just the decay of your exponential curve. I'm not too sure why it doesn't match with the solutions. I'm not too sure if I got something. Am I interpreting something wrong? But I think you should get the idea from what I'm talking about lah. Yeah. How long after t equals 0 will I across R have the value this? from there you can just solve lah, basically. Yeah, it's not too difficult. I'll update you guys again if I realize what I did wrong, if what I'm doing is wrong. But I'm pretty sure when this thing is gone, this thing should just discharge. Yeah. So I'll update you guys again if I'm wrong. Sorry about the confusion, because I think I might be a little bit crazy. The second question to go through is 4, I believe. Yeah, oh, it's this question. So, where's the thing? Okay, so this question, we have 3 identical capacitors that are placed in series and you charge with a battery of EMF. So basically, each of these initially have voltage this. Then once they're fully charged, right, your battery is removed and then subsequently 2 resistors are connected like this lah. So then they're connected like this. And then what you want to do is you want to find the heat that's dissipated across each of the resistors after a long time. To calculate the heat dissipated on the resistors, right, basically you're just taking the difference in energy lah, because obviously the energy must have went to the heat. So, and obviously it's symmetric, so it should actually be the same. But how we do it is that we just need to consider the charges on each of the plates initially. So initially, oh wait, okay, sorry, I interpreted it wrong. My bad. They actually meant this, because they were placed in series like this, right? Like this. Yeah, initially it was like this, epsilon. So actually the initial potential differences are like this. So what we're going to do is we label the charges on each of the plates. So the plates are going to look something like, the charges are going to look something like this. Yeah. And this is the initial charges. Then what we're going to do is that we're going to say this is t equals 0. And after a long time, so let's say t approaches infinity, what we're going to do is that we let the charges on each of these plates be this instead. Q1 minus Q1, Q2 minus Q2, Q3 minus Q3. So something like this, right? The thing to note is that the thing is that once you reach t equals 0, right, you're at steady state. So currents are at 0. Your currents are 0, which means that these resistors are basically shorted, kinda. Since your current through is 0, right, there's no potential difference between the resistors. So these things are basically shorts, and we can ignore the resistors. Yeah. So what exactly does that mean? That means that the potential at the points that are connected by the wires are actually the same. Because, yeah, again, it's equipotential. So what exactly does that imply? Since these 3 points are equipotential after a long time, since they're connected by this wire, this must mean that the charges are the same, actually. So that means Q1 is minus Q2 is Q3. Yeah. So now we actually have the relationship between the charges, right? And another thing is the conservation of charge. The conservation of charge tells us that Q1 minus Q2 plus Q3 is actually this value, because initially t equals 0, these 3 summed up to this, and obviously the charge along this entire wire cannot change, so that must equal to this. So then when you solve, right, that implies that your Q1 equals Q3 is epsilon c over 9, and Q2 is minus epsilon c over 9. So now you have the charges on all of the capacitors, right? So all you need to do is that you need to find the change in the energy. So your energy of each of the capacitors is Q squared over C. 2C, right? This is your energy of each capacitor, right? So since all of your capacitors, right, their charges drop by a factor of 3, right? Because this was epsilon c over 3, epsilon c over 9, right? So they all drop by a factor of 3. That means you lost 8/9 of the energy because this thing is a square. So what is the thing that's dissipated by each resistor? Again, as I said, this thing is symmetric, so it's half, right? So each of it is actually 4/9 of the original energy. And the original energy is 3 times this initial charge. Substitute here, right? So this actually gives you 2/27 epsilon squared C. And this is the total energy that's dissipated by each resistor lah. Basically, again, what we did was this actually doesn't involve much of what we talked about, other than the fact that you need to know how the capacitors and resistors work, and that at steady state these essentially act as shorts lah. So in that case, we use charge conservation as well as equipotential points to determine the charges on everything, right? And then we just take the energy that's dissipated by each resistor like this. Yeah. The last part again. Basically what I said is that your charges dropped by a factor of 3, right? If they drop by a factor of 3, and your energy stored by each capacitor is proportional to the square of the charge, that means you lost 8/9 of your energy, right? And that must come from both of these resistors. And this situation is symmetric. That means each of your resistor must have dissipated 4/9 of your original energy, right? So that is 4/9 times your initial energy. Your initial energy is, you have 3 capacitors, and each capacitor had this amount of charge on it. So then you substitute into this. You substitute this, and you get this is your amount that is dissipated by each resistor lah. Lost at the 8/9. Q squared over 2C. This is your initial energy by a capacitor, right? That becomes 1/3 Q squared over 2C, because I already said that the charges all have become a third, right? So that's 1/9 Q squared over 2C. The difference is 8/9. Does that make sense? Yeah. Yeah, it's fine, but yeah, that's basically this question. This question doesn't actually involve much of what we taught today, but you just need to know how charge conservation and equipotential points works. Yeah. The next question is 8. 8. Where is 8? Oh, it's this question. Okay. So this is a Wheatstone bridge circuit. Okay. Basically, what this question says is that you have a bridge that's balanced when you apply some harmonic alternating voltage, and it balances even under variations of voltage frequency. Yeah. But basically the trick is to apply your standard Wheatstone bridge formula on the frequency domain lah. So you gotta remember that in a Wheatstone bridge setup, right, which looks something like this: R1, R2, R3, R4, and you have a connection here, right? And you have something over here, basically. But basically a Wheatstone bridge, right, basically says that if the product of both of these are the same, right, then these 2 points are equipotential, and no current flows through this galvanometer, right? So you can actually apply the same principle, but in the frequency domain for this question. So how exactly do we do that? Let's just convert everything into the frequency domain, right? All the resistances remain the same. So this one is R1. Here, this capacitance becomes 1/j omega C2 as your impedance, right? This becomes R2 plus 1 over j omega C2. This is your R3 and an inductor, right? And this inductor is j omega L, basically, right? So this is R3 plus j omega L. And this last thing is R4. Yeah. So basically all we're doing is we're imposing this we're imposing this like condition that the product of these must be the same lah. And I will not go through the algebra honestly, because it seems quite tedious. Why is it plus? Aren't they in parallel? Yes, my bad. Please ignore the fact that I did that. But yes, this is parallel. So this is 1 over R2 plus. What is wrong with 1 though? I can't erase this. 1 over R2 plus j omega C2. Flip that. Yeah, that's in parallel. This is in series, so it's like this. Yeah. Yeah. So all you need to do is you take this, you take the product, and then you can solve for the. What are you finding? You're solving for C2 and R2. Yeah. And that's not actually too difficult. I won't go through it, but you basically get two equations, right? Because you're given that the balance persists even under variations of voltage frequency, right? So what you do is when you equate them both, right, you eventually have to equate your real part as 0 and your imaginary part is 0, right? So you take this, you take the product, and again, it's just math. I won't go through it, and I'm honestly too lazy. But you get that your R2 is R1 R4 over R3, which is 200 kilo ohms, and your C2 is L3 over R1 R4, which is 0.5 microfarads. Yeah. Again, I won't go through it, but it's just a bit of math. And this applies the Wheatstone bridge concept lah, basically. Yeah, so it's not too difficult. Yes. Next is Q9, which is this question. Circuit below has two equal resistors R and a capacitor C. Your frequency of the EMF source is this. First thing to do, calculate the total complex impedance of the circuit. Okay, that's pretty easy, isn't it? Right. R, this is basically a resistor of 1 over j omega C, right? So the total complex impedance of the circuit is, these two are in parallel, so we get 1 over R plus 1 over R plus 1 over j omega C inverse, right? And here you have your omega is 1 over RC, right? So this thing can be replaced with 1 over R. This thing can be flipped. You get R on the top. Then now you can see we can bring out the R, this thing, and we get 1 plus 1 plus 1 over 1 minus j. This, we can take the complex conjugate, we get 2, 1 plus j, and then here we get 2 plus 1 over j over 2, we flip it, blah blah blah. Yeah, but okay, I'm not too sure if I did the math right, but I already illustrated how you get it. You get 1 over R plus 1 over R plus 1 over j 1 over R, like this, and you should get your answer is R 1 minus I over 2 minus I. Okay, sorry, I meant j. 1 minus j over 2 minus j. This should be your answer lah. That's not too, it's just a bit of math, yeah. Or I guess you can rationalize it. You can get R3 minus j over 5. Yeah. Then, next question says, if the total current through the circuit is written as this, what are I naught and phi? Again, this one is just applying your phasor knowledge, right? So this is your impedance, right?
What?
This is your impedance, right? So your I represented as phasor is your V represented as phasor over your impedance C, right? So this as a phasor is just epsilon naught, basically. So then this is epsilon naught over, so epsilon naught over R2 minus J over 1 minus J, which can be simplified to epsilon naught over R3 plus J over 2, right? And you can simplify this by yourself, but this magnitude is root 10 over 2, sorry, root 10 over 2, because you just take the magnitude and you get e to the I phi, where this phi is tangent inverse of 1 over 3, because you take this component over this component. Yeah. And you have your answer lah, because this is your I naught, basically. And this is your phi, because remember our relationship that this should equate with I naught e to the I phi lah. And that's this basically. Yeah. So this is your value of I naught, and this is your value of phi. Yeah. The last thing they ask is what's the average power that's dissipated through the circuit? Well, remember that from our formula previously, right? One of our formulas was your mean power is the real part of half VI conjugate, right? So let's just do it, right? That gives the real part of half times your voltage as a phasor. Forgot to write the phasor symbol. Your voltage as a phasor is epsilon naught, and your I conjugate is what? This conjugate epsilon naught over R times 3 minus J over 2, right? We take the real part, this J part doesn't matter. So all we get is 3 over 4 epsilon, over 4 epsilon naught squared over R. And that's the average power dissipated through the resistor. See? It's not too bad lah. This is kind of a basic example actually. But yeah, if you didn't understand what I was talking about just now, I hope this clarifies the procedure lah as to how to do it. You have a question? What's the question? Okay, but as I was saying, basically this is the standard procedure lah. Y is 10 cosine omega t plus phi equals 10 e to the power of this. This is the phasor relationship I talked about just now. Where is it? Here. That is basically this lah, right? So I'm converting from the time domain to the frequency domain lah. So we basically equate this to this. Yeah. The imaginary part, this is the imaginary part. There's no imaginary part here because you're converting to the time domain, right? Remember that our definition is that we take the real. Remember that the definition is that you take the real part. So your IT is I naught. Sorry. Your IT is the real part of your I as a phasor e to the I omega t. Sorry, j omega t. Yeah. So your real part is the cosine. Your sine is the imaginary part, which we discard. Yeah. And you take out the omega t. Yeah. So if you didn't get what I was talking about just now about the example, I hope this illustrates you roughly how to do it. Yeah. Next problem is Q10, which is quite bad. I think it's from SPhO, if I'm not wrong. But okay, so the question says, for the circuit shown below, R1 is 3R, R2 is R, C1 is C2 is C, and L1 L2 is L. And the EMF of the battery is E. So initially the switch is closed and the system is operating in a stationary regime basically just means this has steady state. Find the reading of the voltmeter in the stationary regime. So remember that in the stationary regime, right, this is gone, because they are basically open. Oh my god. This is closed, because they're basically closed, right? Yeah. So all we want to do is, bro, what's wrong with this thing? All we want to do is want to find the reading of the voltmeter, right? So our circuit essentially condenses to something like, what does it look like? Let me draw it. This is a V. This is a R1. This is a R2. This is connected here. This is connected like this. Yeah. So it's connected like this lah, basically. And I think it should be quite clear that it is V, I'm pretty sure. Yeah. This basically this voltmeter has infinite resistance, so the voltage it's gonna look something like these if we label the voltages. Sorry. There's no current flowing through here, so it's like this. So then your voltage difference is basically just your EMF E lah. Sorry, I'm drawing it wrong. This EMF like this. So it basically looks like that lah. And your, I'm gonna use E like this. Yeah. So then your voltage, your reading of the voltmeter is E in the stationary regime lah. This one is not too bad basically. You gotta remember that this thing has infinite resistance, so there actually can be no current flowing through this thing. So that means there's no current flowing through this, right? So that means the potential on both of these is the same. And you gotta remember that since this battery here is E, this imposes this difference E0 here lah. So the voltmeter will read E lah. Yeah. Then after that, the switch is open. And what you want to do is you want to find the reading of the voltmeter that's immediately after the opening, right? So what you then need to exploit is again the conditions that we have, right? Get rid of this now. But now this thing is dark. This thing is like immediately opened, right? So what we then need to do is we first calculate the voltage drops first, right? Sorry. Yep. So then, initially, right, because these are closed, right? Let me redraw the circuit again, actually. This is V. This is R1. This is R2. This is E. Yeah. So then, you gotta remember that your inductors are somewhere here lah. So these carry some current I, which is E over R. E over R. Yeah. So these are carrying current. Here is that we're using is that the current through the inductors are going to be the same, like right after, right? So using this, we can then calculate the voltage drops through the resistors initially, right? Because these capacitors are going to basically act as closed initially, right? So these currents are going to flow like this, right? We're going to have this flowing, sorry. Because of this, right, we're going to have these current flowing through here to be E over R, right? So then the voltage drop across this, right, is E, and the voltage across this is 3E. because of the resistances, this one being 3R, and the resistance here being R, right? That means that your voltage drop, your voltage that this voltmeter is going to display is -2. The voltage across this voltmeter is going to display -2E actually. Yeah. So this one is not too, this one is also kind of simple. Yeah. Because this one doesn't actually involve any time dependence lah, but you basically just consider the currents through everything lah, basically. Yeah. And the last thing we need to do is we need to find the total amount of heat which will be dissipated on each of the resistors after opening the switch and until a new equilibrium state. So all we need to do is we then calculate the difference in energy again lah, right? So the equilibrium this time, right, once that the equilibrium is settled, right? Because when you, after you open the switch, right, what you have is that there's no more battery, so everything dissipates to 0 lah, basically. So the energy that's dissipated overall is basically just all the energy that the system has stored initially lah, right? So then the energy that's dissipated, right, E this, right, is half L E over R squared. There's 2 of this because there's 2 inductors, plus the one stored by the capacitor initially, which is half CE squared. Half CE squared, because you gotta remember that the potential difference between here is also E. So that gives us half L, that gives us LE squared over R squared plus half CE squared. That's your answer. Yeah. Yeah, that's the answer. Yep. So this one is not too bad. This one you just need to be, again, it's similar to this question. It's similar to this question like, where you need to consider a lot of the initial and final states, and the energy dissipated usually is just the difference in the energies out. Yeah. And the last question to go through is this one, which is quite a difficult one because it's apparently from a China book also. But no matter for us, okay, right? So the question says n uncharged capacitors are placed at an equal distance apart, and they're numbered like this. And then the area of the capacitors is much larger than the distance between them. So initially you connect one to ground, and then you connect it, and then you connect the source of voltage V, of voltage U, and then let the connector to the source touches these capacitors like slowly lah. So basically what's happening is that, let's say we have 4, right? Initially we connected like this. We connected, we let it settle, then we disconnect it. We connect it like this. We let it settle. We disconnect, etc., 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 like that. Yeah. So what exactly are we looking for now? The first thing I want to look for is the ratio of the final charges of the kth capacitor to the first capacitor. So basically what we got to do is that we consider like everything, like we consider the process individually first lah. Yeah. So the first thing we do is that we suppose that the capacitance between 2 adjacent plates, right, is C. So since they are equally spaced apart, right, let's say these two have a capacitance C. Then this one have capacitance C, this one have capacitance C, etc., etc., right? So that means, right, when the positive terminal of the power source is connected to the nth plate, let's say this is the, so this is the nth plate, this is the first plate, right? When it's connected like this, right, your source is basically connected across like n-1 capacitors in series lah. Like if you think about it, because this one will have minus, positive, minus, positive, minus, positive, minus, etc., right? This is basically like n-1 capacitors in series lah, right? So what exactly does that mean? That means your nth plate will carry some charge lah, that is governed by that lah, right? So if this is your voltage U, right? n-1 capacitors in series will have effective capacitance, which is C over n-1, right? That means your charge that accumulates on this is going to be Q, which is UC over N minus 1, right? So that's your charge on the nth one. And similarly, your charge on the other one is going to be minus Qn, which is minus UC over N minus 1. That's after the first step, right? Then next, right, your second step is that when you disconnect this and you connect it to the n minus 1 plate, right, you essentially have n minus 2 capacitors in series, right? That means this is going to carry n minus 1, which is UC over n minus 2 charge. And similarly, the charge over here will now actually be the sum, right? Because by charge conservation, basically. So we have QC over N. How do I erase this? What in the world? UC over N minus 2. Yeah. Sorry, this one is a plus actually. This one actually. Wait, am I crazy? Oh wait, sorry, I got it wrong. My bad. Sorry. I'm trying to understand. My bad. But basically this time, right, you initially have this charge minus N here, right? Looking at it right. Yeah. Right, so let's carry this. Sorry, give me a moment to process this. I'm a little confused. And my sponge plate carries a charge of this. Right, surface carries. What? Wait, what is happening this? What in the world? This question is a little confusing to me, so just give me a bit while I try to process it. I think what happens then, right, is that the charge is supposed to build up in a way. Suppose the capacitance between two adjacent conducting plates is this. When a positive terminal is connected to the nth plate, the source is effectively connected along this. Yeah, that's correct. At the same time, the left surface of the n minus 1 plate carries a charge of this, while its right surface carries this. Charge distribution of all the plates is similar to that of the n minus 1 plate. Yeah, I'm a little bit confused at what this question is actually trying to say. So I'm actually not too sure how to answer it, even though I have the solution right here, because I'm a little bit confused about its interpretation. But again, I think I'll get back to you guys when I figure out what exactly the question is trying to say. So I'm sorry I cannot help on this one, but I'm a little bit confused on what exactly it's trying to say. My bad on this. Yeah. I'll get back to you when I understand the solution lah. Yeah, but I really don't get what this question is saying. Try to interpret it. That's my bad. In the meantime, does anyone have any other questions that they want to go through? Okay, if not, then I think I can end the session here. Again, with regards to the questions I didn't manage to go through, I'll update you guys again in the chat lah. But if not, I think that should end the session for today. Again, I'll update you guys again. Thanks so much for coming. I apologize for the teaching today. I know I'm a little bit stoned, but I hope that if you guys still have any questions, you can message me and I can try to explain it when I have a clearer mind, I guess. Yeah, so just feel free to DM me like if you want, like legit, because maybe my explanation today is not very clear. Yeah. If not, then I guess we can end today's session. If you have any questions, you can still stay back.